So now we talk about changing the order of integration when you have an integral. So we've previously done integrals. You can set up a basic double integral as dA, which you can write as either dx dy or dy dx. We can also set up an integral for the volumes, be a triple integral dv, and then you could set up dx dy dz. There's 6 different orders there. Any integral can be calculated in any order, of course, assuming your function is continuous. Now, if your integral has constant boundaries, it's easy to make the switch. You just make the switch like this. The integral from a to b, integral from c to d of fxy dx dy, just switch it, equals the integral from c to d, integral from a to b, fxy dy dx. And you'll get the same result either way. We've done one of those previously. Okay. Also previously, we had a region, and we're given a function to integrate over that region. And then you had to choose which was the optimal order of integration. You say, do I want dx dy or dy dx? Do I want vertical slices or horizontal slices? All those. So now we're going to consider a case where the integral is already set up, but the order of integration is not optimal, so we need to change it. Yeah. So let's see how to do that in an example. So here we go. So let's say we got the integral 0 to pi, integral x to pi of cos y over y dy dx. So the first thing is, if you try to do this integral, cos y over y dy, you can't do that integral. It's not possible. So in single variable calculus, you have to give up. But here we've got an option. We can try to change the order of integration. So if we integrate dx first, we'd be able to do it. Now the question is, how can we set up that integral? So we've got to work out what the boundaries are right now and how that would translate. Now there's 2 ways to do this. You can either work it out the new boundaries using a graph, or you can work out the new boundaries using formulas. Let's take a look at both those methods. Okay, so using a graph, we get this. So the boundaries on the given integral, x equals 0, x equals pi, and then y equals x, y equals pi. So you can draw those lines in. That's drawn on the right here. And next, notice that y is between x and pi. So that tells you that's sort of the upper enclosed area. So let's see. Yeah. So long story short, we get that enclosed triangle there. So now that we've drawn the region, we can actually just set up an integral like we normally would. Only knowing that we don't, so in the given integral, we've got dy dx on the outside, so those are vertical slices. So we want to switch to horizontal slices that'll give us dy on the outside. So long story short, once you've got your graph, then we know how to set up the integral. So now with horizontal slices, y values range from 0 to pi, and on each slice, x is going to range from 0 up to your diagonal line, so y. So there's your new integral. Integral from 0 to pi, integral from 0 to y, cos y over y, dx dy. All right, and that's the setup. Now, what if you want to do this without graphing? You can just use formulas if you like formulas. Let's take a look at how that would work. So writing all these things down in formulas. So the boundaries on the original integral disappeared for a sec, but here we go. Notice that x goes from 0 to pi and y goes from x to pi. So let's write those down as inequalities. So now we want to compress these all into the same inequality. So you get 0 less than x, which is less than y, and everything's less than pi. Okay. So now we know that we want dy on the outside, which means of our new integral. So that means we want y to have the constant boundaries. So what are the constant boundaries for y? It's 0 to pi. And now we want x to have the variable boundaries. So that means x goes from 0 to y. And those are your new boundaries. So now just set up that integral. and it's the same one we had before. And then, of course, we can complete the calculation from here, but that's pretty straightforward. But notice what happens with the dx on the inside. The integral cos y over y is a constant relative to x. So you just get x times cos y over y. Now evaluate as x goes from 0 to y, and you get y cos y over y minus 0, and this simplifies beautifully. This is just the integral from 0 to pi of cos y dy. Something we can do very easily. Sine y, evaluating from 0 to pi, sine pi minus sine 0, and it all just equals 0. Okay, so there's the basic one. Now we're going to look at a slightly harder one. Same idea, but manipulating to get the boundaries a little trickier. So let's take a look. So we've got the integral from 0 to 8, integral from y to the 1/3 to 2 of e to the x to the 4th dx dy. So first notice that we can't do integrate e to the x to the 4th dx. That is an integral you cannot do. So it's going to be helpful to be able to integrate dy, first dy, so we want to switch the order. Okay. So once again, using a graph, what does this give us? So notice that one of the boundaries is x equals y to the 1/3. So that's an unusual form. It'll be easier if we just solve for y. So y equals x to the 3rd, and that lets us know how to graph. So you get this graph. So you get, let's see, y equals 0 on the bottom, y equals 8 on top. Y equals x to the 3rd is the curve, and then x equals 2. And then the region enclosed is marked there, and now we just switch it around. Instead of dx dy, which means horizontal slices, we want dy dx on the outside, so that gives us vertical slices. Okay. So long story short, vertical slices, so we know that x, you can see from the graph, is going to go from 0 to 2. And then on each slice, y starts at 0 and y ends at the graph. And on the graph, or on the curve, I should say, the non-straight curve, y equals x to the 3rd. And those are your new boundaries. Okay. Now, using formulas, I'm going to fix that typo. Okay. So using formulas, we write down the boundaries and inequalities again. So from the original integral, y goes from 0 to 8, and x goes from y to the 3rd to 2. So get these two inequalities. So this is a little trickier to put together. So we've got to do a little bit of algebraic manipulation. So you could either convert, let's see. So notice that the first inequality has y. Second inequality doesn't have that. It's got y to the 1/3 and x. So we've got to make them match up. You could either make the first one about y to the 1/3 or the second statement about y. Either way, here I chose to make the second statement about y. So that means cubing everything. So y is less than x cubed is less than 8. And now that both inequalities have y in them, we can put them together. So you get 0 less than y less than x to the 3rd less than 8. Okay. Now we know we want x to have the constant boundaries and y to have variable boundaries on the new integral. So this statement, this inequality only has y in it. So let's extract the variable boundaries first. Okay. So the variable boundaries are going to be y goes from 0 to x to the 3rd. So we've got that. And now we want to extract the constant boundaries for x. So throw away y, remove y, and you get 0 less than x cubed less than 8. Obviously, we want to make this a statement about x. So take the cube root. And you get 0 less than x less than 2. And those are your boundaries. And there's your new integral. And once we have this, of course, we hopefully we can complete the calculation. And as it turns out, we can. So integrating e to the x to the fourth dy relative to y is just a constant. So you just get y e to the x to the fourth. Evaluating y goes from 0 to x cubed. So that just gives you x cubed e to the x to the fourth minus 0, blah, blah. So now, integrating this, now we can just do a substitution. So u equals x to the fourth, and then 1/4 du equals x cubed dx. And also changing the boundaries, since x goes from 0 to 2, and u equals x to the fourth, u goes from 0 to 16. So this gives us 1/4 integral from 0 to 16 e to the u du. That's just 1/4 e to the u from 0 to 16. Punch it in and you get 1/4 e to the 16 minus 1. Okay.